So we've been looking at some gravity type stuff, and we've started off with some of the ideas behind gravity, and then we looked at some stuff doing some free fall type stuff, which was just a slight alteration of what you guys already done with DTV and VAT, except the acceleration was from gravity. And then we even incorporated a little bit of drag into it, which is the exact same idea as the friction stuff you guys have done in basic dynamics. So next we're going to look at another part of gravitational type stuff, which is also connected to stuff that you guys have done before. We're going to start looking at what is typically referred to as statics. Basically, we have forces, but we're not actually moving on stuff. And statics is used for lots of different stuff. Now, this is actually used in lots of different places, can be seen all over the place. It's a really, really common type thing. Probably one of the more common places people start thinking about this type of stuff is things like bridges and stuff. That bridges and structures and construction projects where there's huge amounts of forces on the supports and the arches and the cables and all that type of stuff. And you look at the forces acting on it, even though the objects aren't actually moving, you look at the forces and the stresses and the strains and that type of stuff in order to see if they can support the weight and that type of thing. So it can be used for that. I mean, it's even in natural type stuff. For example, like spider webs. There's forces in all little webs and stuff like that, and you can look at the forces on that type of thing. And of course, the actual idea behind like the spider webs going off like this are often similar to like the cables that are used to support bridges and arches and stuff like that. We can even take simple stuff like signs, like little signs that hang off the sides of buildings, and we'll be doing some stuff with signs, and just looking at the forces and stresses and things like the cables and chains that support different structures. So this is sort of what statics is about, is looking at forces but things aren't moving. Okay, so what we can do is we can actually do things like look at like support, like wires and cables and that type of stuff. So we look at support wires and cables, and what of course they're trying to do is they're trying to trying to hold up different things against the force of gravity. So that's the sort of things that we can look at. Of course, we can't do like building structures and like skyscrapers and construction and that type of stuff. That's a little bit past what we do, but we can look at simple things like the signs and stuff like that, like really, really simple ideas, and sort of see how things work. And we can start super simple here, and we'll see how this sort of goes along. So this connects a lot to what you guys have done previously, where we looked at a little bit of tension and that type of stuff in basic forces. Where, for example, you've got a mass of some kind, and you have like a rope or a string or something like that, and you guys would do stuff like where you'd find the forces on the rope and the tensions and that type of stuff. So what you guys would do is, if we want to know the tension in this rope, well, the tension was from the force of gravity or the weight of the mass. So we would just find the force of gravity, we'd find the weight of the mass, and then that would be the tension in the rope. And you guys also did stuff where, if it would accelerate up, we could have more tension. Okay, if it accelerated down, there would be less tension. And you guys looked at things like elevator questions and pulley questions and all that type of stuff. So all the stuff we did in basic mechanics and dynamics is a similar type of idea. The only key difference is here, when we do this type of stuff, we don't have to worry about acceleration. This is why it's called statics. It's not actually going anywhere. So it's more about using the force of gravity to find the tensions in situations, rather than looking at how those tensions change based on acceleration, because we're just going to keep everything at rest. Okay, so let's see if we can work with that. Okay, so let's just take something really, really simple. Here we'll bring a nice little picture of Albert right there, and we'll just start nice and simple. And suppose we have the picture, and what we're going to do is we're going to hang it up. You're going to hang it up with like a string or a rope or something like that. Really, really simple. There we go. And what we're going to do is, maybe let's just make some. Let's say, nice and simple. Let's say this is a 6 kilogram picture, so a really heavy picture, and we want to know what the tension was in that string. Well, it's really simple, and this is like literally what you guys were doing before. The tension is because of the force of gravity from the picture, and if we just sort of did the mg for the picture, it's Around, it can be around 59 newtons, but let's just say 60 newtons, just to make it nice and simple. It's going to be around 60 newtons for the weight of the picture. Well, if that's 60 newtons, then the tension would just be 60 newtons. It's just that easy. So that's really, really similar to what you guys were doing before. Now, what if we change the situation a little bit? What if we took the exact same picture, except this time we supported it with 2 strings instead of 1 string? Okay, maybe something like this, maybe something like this. Okay, same picture. Well, it's not exactly difficult to figure out what the tension would be in the strings. I mean, if it's a 60 Newton weight, and now you have 2 strings, we just distribute it. There'll be 30 newtons in this one, and 30 newtons in this one. It's just that easy. The 2 strings will distribute the weight between them. Okay, well, what if we change the situation a little bit again? What if we take the same picture, except instead of having it with 2 strings going straight up and down, what if the 2 strings are not straight up and down? What if the 2 strings are maybe something like this? You'll sometimes see pictures or things hung up by a couple cables or ropes or something like that, and it's suspended like this. Well, now what would the tensions be in the strings? Well, this is a little bit different. Once again, we still have, same way we had 60 newtons going down here, we got like 60 newtons going down here. That hasn't changed at all. And the same way over in the first situation, we had 60 newtons going down, the rope pulls up with 60 newtons. Well, here's 60 newtons pulling down, 30, 30, 60 newtons pulling up. Here we got 60 going down. Once again, we have to have 60 going up. But the ropes or cables, whatever they are, they're not just pulling up, they're also pulling sideways. But that doesn't mean the up part doesn't exist. This one still is pulling up with 30, and this one is also pulling up with 30. Now, we'll assume that they're at the exact same angle, all nice and symmetrical. Those 2 cables still have to pull up with 30 to balance off the 60 going down. But they're not just pulling vertically, they're also pulling horizontally, which then introduces more tension in the ropes or cables. So the vertical part still exists, but there's also now a horizontal one. This one is pulling to the right to balance off this one's pulling to the left, and this one's pulling to the left to balance this one pulling to the right. So they're actually pulling against each other, causing this horizontal tension to be introduced, which then increases the overall tension in that cable right there. Okay, so let's go through some numbers here and stuff that, and we'll sort of see how things sort of piece together. So I'm going to take this right here. I'm going to copy it and move it down here, give it a little more room, and we can see how things go. I'm also going to make it a little bigger. There you go, something like this. And we'll sort of see how these things can kick in if we have some more values. So let's say this is a, let's say 25-degree angle. So this would be a 25-degree angle. So this would also be 25 degrees, 25 degrees. Some people like to use the angles down here. Some people like to use the angle up here. It doesn't really matter for what we will be doing. Now you already know that this is the force of gravity pulling down there. And because that one's pulling the 60 down, we've got the 2 30s pulling up. And there's different ways this can be labeled, but what some people do is they will label this as tension in the y direction, and this is tension in the y direction. And there's 2 ropes, so rope number 1, rope number 2, and those 2 tensions, the 30 and the 30, have to add up to the 60 going down. So basically the tension in the y for both of them have to give you the force of gravity, because it's the force of gravity pulling down that actually creates it in the first place. But what about the sideways ones? Well, we've also got tension going sideways, and some people like label this as tension number 1 in the x, and this would be tension number 2 in the x, and tension number 1 in the x has to be equal to tension number 2 in the x, because it's not moving sideways, and they're pulling against each other. It's like a Newton's third law type of thing. One's pulling left, so the other one pulls right, the other one's pulling right, so the other one's pulling left. They have to balance each other out. So those 2 tensions have to be equal to each other. Okay, so we have the 30 over here, we have the angle. It's just a right triangle. That's all this is a right triangle. So we can sort of piece together what the other things have to be. So again, I'm going to just take this right here. I'm just going to copy and paste this a little bit over here. Copy, paste. There we go. Lost a little bit, but that's okay. It's just a right triangle. That's all it is. So we've got the 25-degree angle over here, 25 degrees. We've got the vertical part here. That is the 30. I could find out the tension, the X, and I could also find the overall tension in the rope itself. And it's just basic trig. We've got the 25, we've got the 30. So if we use sine theta, we could find the tension in the actual rope itself, or sine theta to find that. We could also use tan theta to find this. It's just a basic trig. So if we wanted to find the tension in the x direction, we could use tan theta because we have the opposite. If we wanted to know the actual tension in the actual rope, we could use sine theta to figure that out. Or if you had the x and the y, you could just use Pythagoras to figure out the hypotenuse. It doesn't make any difference. It's just a right triangle. Okay, so let's use our little trig here to figure out those two sides. I'm just going to get rid of that little angle right there. There we go. Okay, so if I use my sine function, I've got the opposite in the angle. If I use my sine function, I can find out that my hypotenuse is around is around 64.3 newtons. That's my hypotenuse right there. So then I could find use cosine if I want to, or use Pythagoras and subtract. It doesn't matter how you go around. It's just a right triangle. And you can get the tension in the x direction is around 58.3 newtons. So since this thing is nice and symmetrical, all the angles are the same. They're both pulling up with 30. Both of these guys would be pulling to the side with like 58 there, 58 there. They have to be equal. And tensions in both of these would be, this one would be like 64 newtons, and this would be 64 newtons. So those tensions would also be the same because everything is nicely, perfectly symmetrical. Okay, so it's very similar to what you guys have done previously, just breaking apart forces and adding them up and making them equal, and that's it. The big thing is the vertical tensions come from gravity. The horizontal ones have to be equal to each other because it's not moving sideways. In fact, nothing's moving here. We don't have to worry about net force or acceleration. The net force is 0 because this is statics, and that's sort of how statics works.